Our session. Good afternoon, dear colleagues and guests. Let me declare open a session of the Dissertation Council for the Defense of Thesis by Aleksei Vladimirovich Siasko for the degree of Candidate of Physical and Mathematical Sciences, Academic Specialization 010408, Plasma Physics, on the theme, the influence of thermal, kinetic, and radiation effects on constriction of a glow discharge in inert gases. Please be prepared that now I have to read quite a number of formal documents, but that's the procedure of our university. Under order, St. Petersburg University of the 18th of March this year, me, Timofeyev Nikolai Alexandrovich, Doctor of Physical and Mathematical Sciences, Professor, Head of the Optics Department of St. Petersburg University, was appointed Chairman of this Dissertation Council. Same order appointed members of the Dissertation Council, and let me introduce them to you. Yuri Zionovich Yonich, Doctor of Physical and Mathematical Sciences, Professor of the Department of Optics of St. Petersburg University. Yuri Zionovich, can you see and hear us? Thank you. Brzezinski Vladimir Alexandrovich, Doctor of Physics and Mathematics, Professor of the High School of Engineering and Physics of St. Petersburg Polytechnic University of Peter the Great. Vladimir Alexandrovich, can you see and hear us? Yes, I can see and hear you. Thank you. Thank you. Smirnov Alexander Sergeyevich, Doctor of Physical and Mathematical Sciences, Professor, Senior Engineer of the High School of Engineering and Physics of St. Petersburg Polytechnic University of Peter the Great. Alexander Sergeyevich, can you see us? Yes, I'm fine. Thank you. Dirk Urland, Doctor of Physical and Mathematical Sciences, Professor of Leibniz Institute for Plasma Science and Technology, Germany. Dirk, can you hear us?
Yes.
Please say yes.
Yes, I can hear you.
Да, не слышно. And the degree applicant is Aleksei Vladimirovich. All is well. Can you see? Can you hear us? Yes, I'm well. Thank you. Also, the academic advisor of the applicant, Golubovsky Yuri Borisovich, Doctor of Physical and Mathematical Sciences, Professor of the Optics Department of St. Petersburg University, Yuri Borisovich, can you see? Can you hear us? Yes, I can see and hear you. So, dear colleagues, since our session is held in the remote access mode, I invite all the participants to follow the procedure, and in case there's some kind of a technical failure or you stop seeing or hearing us, please inform me immediately so that we could eliminate this technical issue, and so that our meeting could be recorded and broadcast online, and so that we could all see each other. If the connection with me is lost, and the announcement to take a technical break shall be made by Yuri Zinovich Yonich. Yuri Zinovich, do you agree? Yes, I agree. But hopefully that will not happen. And one more technical remark. To improve the quality of communication, dear colleagues, please keep your microphones switched off when someone else is speaking or when the degree applicant is speaking, but please remember to turn them on when you're given the floor. Let me also inform you that our meeting is being recorded and broadcast online at St. Petersburg University website, and the speeches are being simultaneously translated from Russian to English or from English into Russian. The applicant's page currently displays an email address to which anyone during our session, the online broadcasting, can send their opinions or send their questions to the applicant online regarding his thesis and the ongoing scientific discussion. These questions shall be forwarded to me by our technical department, and I shall read them out during the discussion talk. Questions should be related strictly to the applicant's speech and the content of his thesis, and must include full name, position and place of work of the author of the question. Questions that are not related to the scientific discussion, to the discussion of the thesis, or to the text or evaluation of the thesis itself should not be presented. Under the order of awarding academic degrees at St. Petersburg University, candidate's degree, doctor's degree, approved by internal regulations of our university, a session of the Dissertation Council is duly constituted if at least 2/3 of the approved members of the Council are present. But not less than 4 persons. Our Dissertation Council consists of 5 members. All 5 are present in the remote interactive mode. Audio, visual contact, and the degree applicant has been established with all of them. Thus, we have the quorum. I instruct the curator of today's defense officer, the Dissertation Council Activity Support Department, Karpova Natalia Vladimirovna, to draw up the attendance list in which Dissertation Council members present shall be recorded and to indicate their work mode, in this case, remote. Let me set forth the procedure of today's session. First, the chairman's summary report on the main content of documents submitted by the applicant and their compliance with the applicable regulations. Answers to possible questions. Second, a brief presentation of the degree applicant on the key points of his research, approximately 15 minutes. Questions to the degree applicant strictly on his report. 4, answers of the applicant. 6, speeches of all the members of the Dissertation Council with their assessment of the thesis and speech of the degree applicant and questions and suggestions to the applicant. 6, speech of the chairman and his review, approximately 10 minutes for that. 7, final answers of the applicant to questions. This part, I think final questions to the applicant should be asked after each review so that no questions get forgotten. The next, presentation by the chairman of questions to the applicant sent in the course of the scientific discussion during this session at the university website. The questions we receive online, answers to the applicant. Next, speech of the academic advisor of the degree applicant. Next, a discussion by the council members before the open voting. During that period, broadcast sound shall be switched off. 12, open individual voting. The chairman of the Dissertation Council shall count the votes and the results shall be recorded in the minutes of the meeting. 13, a decision on awarding or not awarding the academic degree to the applicant. And finally, closing remarks of the applicant, no more than 2 minutes. Dear colleagues, do you have questions or objections to this procedure? I think there are no objections. So let us proceed. Let us start running this procedure. But before, I kindly request you to switch off your mobile phones so we are not interrupted. Thank you for this reminder. So let me start the session. First, I would like to give the floor to the academic advisor of Aleksei Vladimirovich Siasko, Doctor of Physical and Mathematical Sciences, Professor of the Optics Department of St. Petersburg University, Golubovsky Yuri Borisovich, and ask him to introduce the degree applicant. Just a couple of words, please. Aleksei Vladimirovich Siasko. Can you all hear Yuri Borisovich? Yes, we can. Aleksei Vladimirovich Siasko started as a student, in his second-year student, brilliantly presented his bachelor's and master's thesis, which impressed the commission, got enrolled in the doctoral course, and wrote a thesis, which he presented today ahead of schedule. Thank you, Yuri Borisovich. You'll be given the floor again after the presentation of Aleksei Vladimirovich to give a more detailed outline of his scientific work. Next point of our agenda, Aleksei Vladimirovich, you are given the floor for your presentation, please. You have, oh, I beg your pardon. I have to read a number of documents. This is by Siasko Aleksei Vladimirovich. Academic specialization 010404 plasma physics on the theme the influence of thermal, kinetic, and radiation effects on constriction of a glow discharge in inert gases was accepted for defense by the order of the Academic Secretary of St. Petersburg University on the 17th of March this year. Aleksei Vladimirovich wrote his thesis at St. Petersburg University under the guidance of Doctor of Physical and Mathematical Sciences Golubovsky Yuri Borisovich. The number of degree applicants' applications, which set out the main scientific results of his thesis according to the enclosed list, is 6 in journals indexed in the scientific databases Web of Science and Scopus, 6 publications in peer-reviewed scientific journals from the list approved by the Ministry of Education and Science of the Russian Federation, 0 publications. The applicant submitted to the Academic Secretary of St. Petersburg University a full package of documents of acceptance of his thesis for consideration and defense, and all the documents comply with Article 12, Section 3 of the order. All the documents submitted by the applicant, according to the information are received from the curator, comply with the requirements and are kept in the attestation file. Copies are available from the officer of the Station Council Support Department, Natalia Vladimirovna Karpova, who is currently in touch with us. Before I give the floor to the applicant, do you, Dissertation Council members, have any questions to the applicant, any general questions? And if it is necessary to disclose and review the entire list of documents submitted by the applicant? No questions. There are no questions. Thank you. Now, finally, I can give the floor to the degree applicant. And Aleksei Vladimirovich, you have 15 minutes. Thank you. Good afternoon, dear council members and dear guests. And I'm ready to start the presentation of my work. Once again, let me say that the name of my work is The Influence of Thermal, Kinetic, and Radiation Effects on Constriction of Glow Discharge in Inert Gases. My academic advisor is Golubovsky Yuri Borisovich. Contraction is one of the fundamental phenomena in gas discharge plasma physics, which is observed in the form of a sharp compression of plasma and as currency and pressure increase. And in the image on the left show the constricted discharge, and you can see on the axis there's a constricted cord. The discharge conduction mechanism is quite well studied. When the ionization zone is constricted, and then is narrow is formed. Let's discuss what are the basic mechanisms of constriction. It's known that ionization frequency depends on 2 parameters. First, reduced electric field, and second, degree of ionization. So there are 2 basic mechanisms of constriction. The first mechanism is related to peculiarities of electron kinetics. As the current increases, degree of ionization increases too, which leads to maximization of the function of electron distribution and constriction of ionization zone. A second mechanism is connected with heterogeneous heating of the neutral gas. Since temperature is heterogeneous, is not is not reduced, and since ionization is exponentially dependent on this parameter, constriction may also occur. And the problem now is that there's no unified opinion in a scientific community which of these mechanisms actually leads to discharge constriction. That is why the goal of my work was to describe the phenomenological pattern of constriction in inert gases, argon, neon, and helium. This second was necessary to carry out experiments that would allow to investigate the influence of thermal and kinetic processes. Next, it was necessary to calculate and measure temperature profiles in neon, argon, and helium, and describe the constricted cord. And of course, the most important task was to identify the main mechanism which leads to discharge constriction. And finally, it was necessary to investigate how transfer of resonant radiation affects the constricted discharge parameters. The first part of the report will focus on phenomenology of inert gas constriction. So we use a cylindrical gas discharge tubes, which we filled with argon, neon, and helium. Pressures are shown here, was a fraction of atmosphere. And all images on the left show a diffused state of discharge in all three gases. You may see that fully occupies the tube, and as the current increases, show that constriction occurs. And on the axis, narrow cord is formed. And visually, constriction is identical in all three gases. As we can see, is that in argon, the constricted cord is located near the wall. And if we look at the Wald-Ampere characteristics of all three gases during constriction, we observe a reduction of electric field. And radiation, we look at spectra in all the three gases and of breaking continuum. If we try to measure radiation intensity of the discharge tube, we get the profile of ionization and excited ionization. And if intensity of continuum is related to ionization of charged particles. So it will describe a distribution of charged particles over the radius. So let's see what's happened, the spectral line profile and in the continuum profile. First, let's consider the spectral lines, black dots, points, profile in diffuse discharge in low current, red dots in constricted state. As you can see that all three gases, compression of spectral lines occurs. That means that ionization zone is also constricted. Now let's look at, so we're seeing argon profile of the radiation is compressed, which means the distribution of current channel, electric current passes and doesn't pass the entire cross section of the tube. And in helium, the discharge contract particularly does not change the continuum profile, and that means that current continues to flow through the entire cross section of the discharge tube. This is a fundamental difference between constriction in helium and other gases. The phenomenon is here called optical constriction. Second part of my report shall focus on the experimental study of thermal effects on discharge constriction. Since discharge constriction there are two mechanisms, we needed to carry out an experiment that would separate these two mechanisms, to separate a thermal mechanism to avoid heterogeneous heating. For this, a scheme of pulse modulation, which allowed to modulate current by rectangular impulses, was created. And if from hundreds of milliseconds, gas could not be heated efficiently, And to control the gas temperature, we used interference method. We are based on Michelson interferometer. Let's start with results for neon. In all three gases, we can compare two types of gases. Where the first gas was heated and impulse gas of a small duration. Neon pressure was 90 torr per centimeter. In both cases, pulse duration was 7 milliseconds. So first, let's look how the change in the interferogram looks like. A neutral gas heated in the stationary discharge. The changes in pictures show the change in plasma refractive index. Since in our case, plasma is, so it depends on, determined by neutral particles, is and knowing, using the, so we can reconstruct the neutral particle profile. At the same time, we solve the non-stationary equation of heat conductivity. So let us compare stationary discharge and short impulse. Stationary discharge gas is heated is heated in the center to approximately 600 Kelvin, and in the pulse mode, in the end of impulse, temperature of gas only reaches 350 Kelvin. So we significantly reduced heating of the gas. On the right, you see dynamics of gas heating. And so what's in the picture at the top shows a stationary discharge, a picture at the bottom, impulse discharge. And visually, there is no difference between stationary and impulse discharge. See constricted quote in both pictures. When we look at the profile of summary radiation, the profiles look the same, so we may conclude that constriction in neon does not depend on heterogeneous heating. Constriction in neon is results from kinetic effect. Let's proceed to the second gas, argon. Pressure in argon was 200 torr, and then we compared stationary and pulse modes, and pulse duration was 0.5 milliseconds. Let's look at interferogram. Here you may also see, as in argon, but also we can see in neon, but also we can see. Dear colleagues, can you hear me? Aleksei, we cannot hear you. We stopped hearing you. Aleksei? Yuri Zinovich, yes, I can hear you. I think we must take a technical break because we cannot hear Aleksei. Do you all hear me, dear council members? Yes, we can hear you. Vladimir Alexandrovich, are you with us? Dirk, can you hear? Can you hear?
Yes, all is okay. Thank you very much.
Aleksei, so the problem is on your end. Let's wait. Let's take a break, and we shall add up some time for his presentation. I think something went wrong. Aleksei, he cannot hear us. Maybe. figure 14. We can continue now. Okay. Let us continue. Let's continue. Let me continue my presentation. Now we are. Let's look how thermal effects impact argon. And the drawing you see on the left is the interferogram. Is unlike neon. You see the center of interference circles. So the constricted cord is similar to what we observed in photographs in the discharge tube. So now let us compare temperature. Temperature profiles the stationary and pulse modes. You see in the stationary mode the gas temperature reaches almost 1,200 kelvins, and the maximum temperature is shifted to the boundary, the border of the discharge tube. If you look at pulse mode, in this mode, gas temperature got reduced to 400 kelvins. And the temperature is much closer to the axis. If we look at radiation profiles, we see that they are identical. So which means that heterogeneous heating of gas does not cause constriction. Yet constricted cord in pulse mode again is much closer to the tube axis, which means that heterogeneous heating results to surfacing of constricted cord. We may try to describe this effect of Navier-Stokes equation, thermal conductivity equation, and continuation equation. Now let us compare the results of numerical modeling with those of measurements. You can see that results repeat quite well the numerical modeling, and the comparison given in my thesis shows good match between theory and trial results. So which we of constricted cord in argon. Now let's look at helium. For helium, pressure was 200 torr per centimeter. Discharge current was 100 milliamperes per centimeter. And in my thesis, I compared pulse and stationary modes. So here, let me show in. So we had a reservoir which could be pumped with running water. When we immersed discharge tube, we could at temperature 290 Kelvin. The thermostated temperature, we reduce gas temperature inside. Thus, we can compare two discharges, thermostated and normal. Now, first, again, let's look at parameters of, you may see that radiation spectral lines is constricted. The profile of charged particles goes down, and volt-ampere characteristics, you may see this increase. So what happens to discharge is first black dots is thermostated discharge. When the thermostated walls of the discharge tube constriction disappears. The spectral profile gets wider. Nothing happens to the continuum, and on volt-ampere characteristics, there's no drop, which means that the optical constriction helium results from heterogeneous gas heating, which is different from neon and argon, which again proves helium is different. In helium, unfortunately, we could not take these measurements because the length of discharge tube was not sufficient. So we only made calculations for the heat conductivity and got profiles of gas temperature in the stationary and pulse thermostated wall mode. And knowing temperature profiles, we could restore profiles of a thermostated and stationary discharge, seeing that it is much lower. And from profiles of radiation, we could make electron concentration profiles, and these data, we shall need them later. Let's proceed to the third part. The third part will focus on the constriction mechanisms. I'll start with formation. As we see that in helium, unlike other inert gases, there's no channel is formed, and the death of charged particles causes this channel. At high pressure, practically all ions become molecular because of active conversion, and the speed of dissociation recombination is quite well measured, well studied, amounts to 10⁻⁷ cubic centimeters per milliseconds, and the temperature relation of these processes is also quite well known. If we look at speed literature, which describes speed of recombination of helium, in our opinion, the best work gives the following speed: less than 5 to 10⁻⁻ degree cubic centimeters per millisecond, and is quite vague. This means that the speed of dissociative recombination of helium is quite low. As the main loss occurs on the walls of the tube because of ambipolar. There's no narrow channel unlike in other gases. Now let us proceed to the kinetic mechanism of constriction, which leads to contraction in neon and argon, as connected by solving the Boltzmann equation, and using other electron atom and other collisions. The type of distribution function is will have a main on the type of elastic cross section of electron atom collisions. We know that cross section electron atom in argon grows up to stays in neon, and in helium this cross section goes down. So that what happens what results from differences in cross section. In this picture ABC, we see the distribution functions for argon, neon, and helium at a fixed field value, which correspond to fields in constricted and Townsend's. This shows dependence relation of distribution function on concentration of charged particles, and you can see as concentration of charged particles grows, electron atom and electron collisions, distribution function maximizes in all three gases, but this effect is very obvious in argon and small in helium. Next, we can build a summary frequency of non-elastic collisions depending on concentration of charged particles according to these distribution functions. For argon and neon, there is a transition sphere area, transition area. In helium, this non-linearity is almost absent and is not observed. Next, we can measure the profiles in. So we can. So then we find that in argon neon profile is very constricted, which is similar to what we observed in our experiments. And helium, the profile is quite quite smooth. So this figure shows that the kinetic mechanism quite well describes constriction in argon and neon, but it does not describe constriction in helium. Let's proceed to helium. In helium, constriction is caused by the thermal mechanism. As you remember, in the previous part, we recreated profiles of charged particles in stationary and profiles of reduced fields. And knowing these values, we can look at how the distribution function over the radius of discharge tube changes. And we can see that the effect of distribution on the radius is very small. And this effect is to see radiation profiles and compare them. Red lines, these are radiation profiles from theory, and red dots, these are spectral lines of radiation. In the thermostated mode, theory provides diffuse radiation profile, which agrees with experiments. And in the stationary discharge, radiation profile is constricted, which also agrees with the test results. Thus, the thermal mechanism well describes constriction in helium. And the fourth part shall be devoted to analysis of the effect of resonance radiation transfer on the constricted discharge parameters. The non-equilibrium plasma is one of the main mechanisms of destruction of excited particles. And if absorption is large, then radiation may not immediately leave plasma, but it can be absorbed, and then radiation may reoccur. And can't hear the speaker at all. Is observed of constricted discharge. Yes, the scheme, we can see that the balance is made by radiation emission. Operator of radiation transfer consists of two members. The second member describes here the nuclear of integral operator, describes probability of photon emitted will pass and be absorbed. There are different methods for solving the equation of resonant radiation transfer. Approximation is Biberman is or effective time of Hallstein. So what is the essence? It is both assume that concentration of excited particles changes smoothly along the radius, and then concentration of agitated nucleus of the integral operator. And the disadvantage of this method is that it cannot describe redistribution of excited particles. And our group is developing accurate methods, the matrix method. The essence of matrix is plasma volume at small cells, and then inside small cells, and then we can integral operator radiation transfer with some matrix elements which describe the probability of absorption, photon absorption. So these two ways to solve the equation were used in collision radiation, which describe discharge constriction in argon as ground state for stable resonance levels, 10 excited levels. So we also considered ions and heterogeneous gas heating. Discharge results were 96 torr per centimeter and 0.5 to 20 milliampere per centimeter. And as this figure shows some results of our modeling, the following dependencies are shown: concentration of electron on the axis, concentration of metastable resonant items, the current code and electric field. White dots correspond to reduced solution. Black dots is exact solution of the equation. And at a small value, current values, when discharge is diffused, both solutions provide similar results, which is logical because in diffused state, plasma components are smoothly go down on the tube radius, and the changes are obvious in constricted state. Transfer of resonance radiation leads to reduction of concentration of charged particles on the axis, and also to widening of the profile of the current channel. And these results show that radiation transfer seriously affects parameters of constricted discharge. When plasma components are very constricted, their profiles differ from the radiation and modes. Thus, in conclusion, we demonstrated that constriction of helium is different from other inert gases. We proved that heterogeneous gas heating is not the main constricting mechanism in neon and argon. In these gases, it's called by peculiarity of formation of electron distribution function. For the first time, we described this subsurfacing of constricted core in argon surfacing, and we showed that in helium, in contrast to neon and argon, it's caused by heterogeneous heating of a neutral gas. And in the end, we demonstrated impact. The main results of our work were published in 7 articles in journals indexed foreign scientific databases. Thank you for your attention. Thank you, Aleksei. Please switch the microphones on. Questions, please. Yuri Zinovich, please. I think in slide 4, there was showed a relation between the field and current. 4, I think. Slide 4, I think. Or this one. It's okay. This one is okay. You call this volt-ampere characteristic, but it is not. This voltage should be, but that is not important. My question is different. How did you measure? In all 3 discharges, we measured voltage, anode. Aleksei, we cannot hear you well, and then we measured anode and cathode decrease. Can you hear me now? Yes, we can hear you better, but the beginning, we could not hear the beginning of your remark. In our experiments, we measured voltage between anode and cathode. Then we measured anode and cathode decline and divided it by length of a positive column. Since we didn't have zones to measure the positive column. And how did you evaluate anode and cathode? How was it measured? Не слышно ничего. Have in literature. I see. Okay, thank you. Did you hear me? Aleksei, thank you. More questions? Aleksei, I have the following question. Relative concentration by cross section. What was intensity of this Bremsstrahlung, and electron concentration was quite good. Thank you. More questions, please? If no one has questions at this point, thank you, Aleksei. Would any of the Dissertation Council members like to say something, add something? No. I can say a couple of words. Please, Yuri Zinovich. Since I also working in this field, I watched Aleksei's work, and also always had a high opinion of his approach and of his results. And at the department, at our department meeting, his work aroused lots of interest. And that's all I wanted to say. Thank you, Yuri Zinovich. Does anyone else want to speak? In that case, thank you. We don't have any external reviews. That is why we can proceed to reviews of each member of the Dissertation Council with their all reviews were published at university website. Can you hear me, colleagues? All reviews were published at university website. That is why I suggest not to read reviews, but focus on the most important points, especially significant, and of course questions, and final assessment of the work. Do you have any objections? Thank you. Then let us. And also one more thing, I suggest that degree applicant should answer the questions right after which review is presented. Yuri Zinovich, your review, please. I will not read my entire review. Just a couple of words. I would like to say that constriction is a very interesting process, which has not only scientific but also applied significance, and lasers it's impossible to obtain high energy because of constriction, which later leads to and then it doesn't help. There's no way. And as for mechanisms, indeed, it's Yuri Borisovich demonstrated with 100% certainty that in neon and argon, the constriction mechanism is non-thermal. But these were old works written in 1980s, and since that time experimental potential grew much better, and what Aleksei obtained, this is a great contribution to understanding of what happens, getting detailed, reliable results. But most of all, I was impressed by the measurement of temperature fields with the help of such ental as Michelson interferometer. And so this combination gives excellent result. So that was very good. And the calculations possible with the help of modern computers are also impressive. But, well, and yes, as for neon and argon, it was more thorough understanding. As for helium, results are absolutely new because it was not clear what happens with helium. The mechanism was obviously different from neon and argon. And here the author obtained new important result. And thermostating has such a big impact. At that, I shall finish the positive part and will read my questions and remarks. My first question is, transition of discharge from diffuse form to constricted form occurs in a jumpy manner. So you can see, and for neon and argon, this can be explained by switching of electron death mode from non-local diffusion to local recombination. How can you explain the presence of this jump in helium, where constricting is caused by the thermal mechanism? And so that's my question, my first question. Or maybe this is a remark, because I did not find a good explanation for this in your thesis. And next I have remarks which are quite minor, but because the work was very interesting, so I read it very carefully. That is why I'd like to make these remarks. So first, in describing the interferometric method for measuring gas temperature, the author refers to previous works by American authors, references 81 and 82. I think it would be appropriate to mention articles. This scientific academic advisor of the thesis by Golubovsky, Kagan-Rzhevsky, published in 1974, and Golubovsky-Rzhevsky, Florko, published in 1974. Next, I have there's one statement which I think is not quite accurate. Page 42 says, in large area of electron concentration values, plasma can be considered ideal gas, which makes it possible to determine the value of the temperature of electrons from the ratio of average kinetic energy. And here, I don't, what do you mean by determine here? Determines calculate. And if we calculate, then here you need the Maxwell distribution function, ideally. And then there are some inaccurate expressions I will not list. Of course, I see that, but and finally, as already mentioned, the fact that the work is very well written, but sometimes you may come across some language issues. For example, Aleksei likes the word neutrals. I understand that neutral, there's no such word in the Russian language. And if we mean atom, and then we need molecular gases, but here he means atoms. So neutrals means atom. So why not use the word atom instead? And neutrality is always emphasized where it is not necessary. For example, page 79, 80. There's totally 6 times neutral gas, 2 times neutral atom, and 2 times neutrals are mentioned. I think that is too much. And Here, let me give two more examples as a common thing. It's page 41. Substituting expression for a condition operator, the kinetic question will take the form and once again. But these are these remarks are of private nature and in no way detract from the already noted high opinion of the work, the thesis by Siasko, Aleksei, the influence of thermal, kinetic, and radiation effects in constriction corresponds to the key requirements set by the order on the 1st of September 2016, number 6821/1, on the order awarding academic degrees at St. Petersburg University. And the degree applicant, Siasko Aleksei Vladimirovich, deserves to be awarded academic degree of candidate of physical and mathematical sciences, academic specialization 010408, plasma physics. Clause 11 of the above-mentioned order has not been violated. Thank you. Thank you, Yuri Zinovevich. I suggest Aleksei I suggest you don't read the article, just say that it corresponds and you agree with awarding the degree. Do you have any objections? If no one has any objections, Aleksei Vladimirovich, please answer Yuri Zinovich's comments. As for the first comment about a course of jump-like constriction, where the aim of my work was to identify the mechanism, and indeed in helium the mechanism is not kinetic but thermal, and at that same time the explanation, interpretation of the jump-like nature requires further experiments and theoretical explanation, but I may suggest about the nature of this jump the theory of thermal explosion. According to under this theory, if locally emission of heat exceeds the temperature may jump up. And when temperature increases like this can result in a dramatic change of the electric field. And maybe that will explain the jump-like transfer of constricted helium. As for the second comment, yes, indeed, it was necessary to add works of our scientists, especially where Yuri Borisovich was the author. Here I agree with Yuri Zinovevich. As for the third comment about the electron temperature, thus we set electron temperature, and Yuri Zinovevich correctly observes that this relation needs a balanced function of distribution. But when it is not balanced, this equation, we just add a multiplier which is almost equal to 1. That is why we used this relation. And let me answer the last two comments together. Yes, I agree. Yuri Zinovevich, thank you, Yuri Zinovevich, for noticing typos in my thesis. Thank you for your review. Thank you, Aleksei Vladimirovich. Yuri Zinovevich, are you satisfied? Yes, quite satisfied. Thank you. Next, I would like to give the floor to Vladimir Alexandrovich Rozhansky. Can you hear me? Yes, I will not tell you about the contents of the thesis as we agreed. I'd like to say one thing. I was very impressed by the thesis. The work is well balanced. It has very convincing experiments and high quality calculations. And this is a rare thing today. and this thesis has both, and both done quite well. And as I was reading the thesis, I was very surprised why such a classical problem, the difference in constriction, has not been dealt with. And so finally it was solved by the author. The constriction in helium, occurs because of one mechanism, and in other inert gases, the mechanism is different. And this makes a very good positive impression. And so I will not repeat, so we'll proceed straight to critical remarks. The work addresses numerical equation of electron-electron collisions, and the credibility is proved with having numerical codes. This is quite convincing, but at the same time, it could be supplemented by other methods. For example, there is the Mms method. By the Mms method, you take a complex equation and the analytical solution similar to what you expect, and in analytically there appears an additional member. This is done analytically, and then with your numerical methods you can reproduce the solution of this analytical solution of the modified equation. The credibility arises, no doubt, and you don't need any numerical codes, because these numerical codes will be compare your. So I suggest you apply this method in the future. Next comment is about, though you quite convincingly prove that electron collision frequency is the parameter that leads to the change of the discharge nature for two inert gases, it would be good to see their numbers. So when comparing a neutral collision frequency, the discharge modes change. And finally, third, the model of radiation transfer, developed in the thesis as better than Holstein method. This impressed me. So I'd like to say here that this activity could be in demand of ITER demo reactors, tokamak type reactors, where on the one hand reactors are growing bigger, and on the other hand pressure increases. So the method described in the thesis could get some practical application. So that is is probably a suggestion. But generally speaking, as I said, the thesis made a very good impression, and I strongly support awarding the academic degree of candidate of physical mathematical sciences in academic specialization plasma physics to Aleksei Vladimirovich. Thank you, Vladimir Alexandrovich. Aleksei Vladimirovich, will you please answer? Vladimir Alexandrovich. Thank you, Vladimir Alexandrovich. As for your first comment, indeed, verification of by comparing with Bolsich Plus package and this artificial solution method. I have not used it earlier, but it seems to be very interesting, because in that case data verification may occur without measurement results or results from other models, which is very interesting. So in the future I will certainly try to use it. And as for your second comment, we, when making the presentation for the thesis, I took into consideration the well, this omission in the text of my thesis, and now let me show you a slide where you see frequency of non-elastic collisions depending on concentration of charged particles for helium, neon, and argon. This figure was included in the thesis. And argon is an example. Electron frequency multiplied by mass. And you see that this transition area, frequency of electron-electron collisions, becomes similar to frequency of electron-atom collisions. So you see the transition, and electron-atom collision becomes similar. And as for your third comment, I absolutely agree with this comment that this method for correct accounting of radiation trapping can be applied to different plasma sources and built in the most common software packages. And our group tried to apply for a grant for implementation of such method of solution, but unfortunately we were not awarded this grant. That's all. Thank you. Vladimir Alexandrovich, are you satisfied? Yes, I'm quite satisfied. Thank you. Thank you. And Alexander Sergeyevich, the floor is yours. I would like to praise the thesis. It's been a long time since I came across a thesis where something is so well explained, where temperature, impact, and impulse mode is used. Most people would simply calculate the heating time and say it's longer than the impulse duration. So here calculation, compare temperature comparison. So this makes a very good, very positive impression. And I'd like to say that the thesis deserves to be awarded the degree, and I'm going to vote for. As for the critical comments, which you can always find if you try hard enough. So here I have two comments. First, in chapter 4, the author shows that in neon and argon, the transition in the constricted mode starts near cathode and spreads towards anode, but the mechanisms of this phenomenon are not described, why it starts near the cathode and spreads towards the anode, which would be interesting to know. And secondly, also a small comment, when analyzing the influence of different constriction mechanisms in chapter 5, the author discusses dependence on distribution function exceeding the first potential. Yet constriction obviously is connected with increase in concentration of charged particles, and naturally it would make sense to analyze the increase not only of the distribution function, but of increase in ionization frequency, which maybe relate differently to rather than general number of collisions. But these comments, of course, do not affect the overall positive impression. And I also invite everybody to vote for awarding the degree. Thank you, Alexander Sergeyevich. Aleksei, will you please answer Alexander Sergeyevich? Thank you, Alexander Sergeyevich. As for your first comment, in chapter 4, when we discuss how stratification of discharge constriction happens, we studied development of constriction of discharge stratification under Golubovsky-Borisovich. Was conducted Vladimirovich Nekuchayev in St. Petersburg University, and in his work he showed that the depending on conditions, pressure and current, the wave can spread from anode to cathode direct, and reverse waves may also from cathode to the anode. Also, there were cases where two waves propagated simultaneously towards each other, and moreover, there were cases where pressure was close to atmospheric, and constriction discharge stratification occurred almost instantaneously along the entire length of the column, of the positive column. Such unusual picture for its interpretation is creating the model of the positive column of final length model should take into consideration anode and cathode areas. And such work, of course, will be very interesting, and so maybe that will be subject to my future study. As for your second comment, I absolutely agree that it would be better to analyze ionization frequency, but at higher pressures, where step processes prevail over direct processes, the non-elastic frequency does not coincide with the ionization frequency, but ionization frequency is proportional to excitation frequency. And quality of results we show in chapter 5, they do not depend on us considering summary frequency of so that it will not, there will be no changes. That's all. Thank you, Aleksei. Alexander Sergeyevich, I am satisfied. Thank you. Now I would like to give the floor to Dirk Urland. Dirk, please present your review.
Yeah, thank you very much.
Большое спасибо.
I'm also very impressed by the work, and I want to point out only some things here. So what a particular benefit of the work is a close combination of many different experimental studies with theoretical models. So I was really very impressed from this, and also that Mr. Siasko could obtain a very close agreement of the theoretical and the experimental results. So that gives really very interesting findings, especially for the property of constriction in helium, and also for the action of the temperature dependence of the thermostatic regime in comparison with pulsed regimes and so on. So that was really very interesting for me to read the work. But I will come quickly to the questions. I have 3 questions, and that are only some smaller points, of course. But what I want to ask in the beginning is there might be a typical also some instability of a constricted discharge. That means some movement, some change of the discharge in time and in space. And especially if you look with a spectrograph or with a CCD camera from the side then there might be some movement, and there might be so one have to care about some uncertainties maybe of the position and of the radial profiles. So I ask you to comment on this a little bit. My second question is connected with this. So what I miss in the work is a little bit a discussion of uncertainties, experimental uncertainties or errors. So you give errors for the gas temperature, but of course it would be also interesting to know how accurate are the radial profiles of radiation intensity, and especially also of the continuum radiation, because you determine even the electron density from the continuum radiation. And the third question is, what I a little bit miss in the work is a discussion of the radial electric field or the radial, the electric potential distribution in the constricted discharge. So for me, it's a very interesting point to know what's happened with the electric potential outside the constricted column. So that are my three questions. So altogether, I was very impressed by the work, and there's no doubt that I propose granting of the candidate with a degree of candidate of physical and mathematical science. Thank you very much. I hope it could be translated, yes?
Aleksei, please answer questions of Professor Urland. As for the first comment, yes, indeed, constricted discharge often is unstable, and here the main solution that we used was using a scheme of impulse currency modulation, and as was described as I described in my thesis, we used a scheme not from zero level, but maintain a working discharge, and using this scheme eliminated all instability of constricted discharge, which resulted in good possibility to reproduce the results, and error on result reproducibility was smaller than the error connected with interferometer. As for, I remember you asked about limitation of the Ccd camera, the use of Ccd camera. Here the main drawback of our scheme was that our Ccd camera was without amplifier, and so during exposition was limited by hundreds of milliseconds. If we increased exposition, the camera was non-sensitive to radiation, and if we made exposition over 100 milliseconds, then we could not see the structure of constricted column. It's talking of measurements we made on the side of the discharge column, and to study constricted and stratified discharge. As for the second comment, we measured profiles of spectral lines and of continuum. And speaking of errors, the relation signal to noise when measured in profiles of spectral lines was approximately 0.01, and measuring continuum, the value was about 0.05. In interference measurements, the error did not exceed 7%, and the error in temperature measurements are representative for all the temperature measurements. And as for your third comment, it is possible to calculate potential profile of constricted discharge and distribution of discharge in space. And for that, discharge, we considered molecular films and flows of the charged particles, making them equal to radial electric field, which is described here with ion mobility is much higher, and mobility of electrons is much higher than mobility of ions, and diffusion is much higher. And knowing that field voltage is, we can find the radial profile of potentials, which is shown here for constricted cord. A profile of charged, so you can see the profile of electric potential. And to complement Poisson equation system, you can see charge distribution. So if we know, we can also find ion distribution in entire volume of plasma. Quasi-neutrality condition is quite well observed, and you may see on the right, on a bigger scale, only on the edges of discharge tube where ion concentration is higher than electron concentration. That's all. That's all, Aleksei. Thank you. Professor Uland, are you satisfied with the answers?
Thank you very much. I'm satisfied. Very good answer.
Thank you. It's time for me to present my review. I absolutely agree with the previous speakers. I think the work is excellent. And let me make some small critical remarks. I am a little bit younger than Yuri Borisovich Golubovsky, but as I remember that Yuri Borisovich always worked on constriction, and each new work added something and finally the constriction in inert gases mechanisms are well studied, and Aleksei did this brilliantly using a wide range of experimental methods, which I would like to emphasize, especially because when you study, when a researcher is an expert on plasma physics, not always optical, spectral, interference methods and different methods of the charge generation are used. So all the methods which enabled Aleksei to show very convincingly that the mechanism he described are essential in this, essential for constriction. Also, I'd like to mention one thing. Together with his academic advisor, Aleksei is very active. And just a small touch, maybe 2 months ago, there was a platform called International Low Plasma Community. Maybe colleagues are familiar with this. So the platform was created so that in present situation where all conferences, meetings, symposium have been cancelled, to make physicists to communicate. The platform was created by 2 Americans. You can join this platform quite easily, become a member of this international low temperature plasma community, and already 2 issues have already been released. And in the second issue, there is data presented by Yuri Borisovich Golubovsky and Aleksei Siasko. So if you access this platform, you will see magnificent photos which show constriction, how discharge surfaces and how it is constricted. I know Aleksei's work quite well because it was performed at our department. And we were always in touch with Yuri Borisovich and Aleksei. He presented his work at the department. He made presentation at a session of the Department of Physics, and he won a prize. So it was hard for me to think of any critical comments, and in the end, I could find only one critical comment in Russian literature. Tor is spelled with one R, and you spell it with two R's. I think you confuse it with the English spelling. Though, of course, this comment may not have no impact on my opinion, and I think the applicant deserves to be awarded the degree, and I encourage everybody to vote for awarding the degree to Aleksei. Thank you. So maybe someone has questions or would like to speak. Aleksei, would you? I forgot. Would you like to answer my comment? As I was writing my thesis, I wondered how to spell this word with one or two R's. And in the end, I started searching literature, and I came across both variants. So I decided I'm satisfied with your answer. Thank you. I have a question to Natalia Vladimirovna. Do we have any questions to at this point? There are no questions to Aleksei. Thank you. That's good. Thank you. Yuri Borisovich, I would like to give the floor to you, academic advisor, Professor Golubovsky. Thank you, the chairman. The work Aleksei uses experimental methods. He knows modern experimental equipment very well, and together with experimental skills, Aleksei proved to be an excellent theoretician who can model plasma at modern level. Secondly, as a comment, over decades, I've been working on discharge constriction. I could have solved all the problems over the years, yet as a speech of Alexander Sergeyevich, there is another fundamental problem. Why constriction starts at different ends of the discharge tube. Endless positive column theory has been created, and so the theory should be updated with regarding the electron phenomena. An interesting comment, for example, constriction in neon and argon happens at hundreds of milliseconds or milliseconds. And in helium, for constriction, you need to hit the walls of the discharge tube to approximately 2 minutes. And so, Yuri Borisovich, I apologize. Now you have to you please tell us about the degree applicant. So what I'm trying to say is that the subject for future research after this defense we have already identified, and the degree applicant can cope with these challenges in near future. His ability is really impressive. Thank you. Thank you, Yuri Borisovich. I have a question with a full informal comment. Since our session is being held in the remote access mode, and maybe communication was not very good, but I think everything is familiar. Maybe anyone has any unanswered questions, or maybe some points that need clarification. Would anyone want to ask any questions? Any more questions? No. I say I judge by your silence that you have no unanswered questions. Then, colleagues, we should proceed to the voting procedure. This procedure can be, so we can switch the sound off and only discuss among the members of the Decision Council and then proceed to open individual voting. Or if we don't need any time for a private discussion, we can proceed straight to voting. So what is your opinion? What do you think? We can proceed straight to voting. I think that makes sense because I think we all share the same opinion, and so then but we have there's no disagreement. That is why I put the question of awarding the degree of candidate of physical and mathematical sciences, academic specialization 010408 plasma physics, to Siasko Aleksei Vladimirovich to the open individual vote. Let me remind you that a decision of the Dissertation Council on awarding the academic degree shall be considered positive if more than a half, but not less than 3 members of the Council present at the session voted for it. Yuri Zinovich, your opinion? Are you for? I'm for awarding. I'm for. Thank you. Vladimir Alexandrovich Rozhansky, your opinion, please. I'm for awarding the degree. Yes, thank you. I put my hand up. Thank you. Alexander Sergeyevich Smirnov, your opinion? Thank you. I'm also for awarding the degree. Thank you. Dirk Orland, your opinion, please.
Yes, I'm for awarding.
Thank you. I'm also for awarding the degree. Thus, the decision is unanimous. All 5 members of our Dissertation Council voted for awarding the degree, and thus the decision to award to Siasko Aleksei Vladimirovich the degree of candidate of physical and mathematical sciences, academic specialization 010408 has been made. Dear colleagues, since our meeting was held in remote access mode, I have to ask you again, do we have any questions or comments regarding the procedure? No. No comments and no questions. Thank you. And the final stage of our meeting, Aleksei Vladimirovich, time for your closing remark. Thank you very much. I would like, first of all, to thank all the members of the Dissertation Council for their work, for sharing, for spending their time, for reading, giving their time to reading, and giving their time to my work. Thank you very much for this. Also, I'd like to thank all the employees of the optics department of St. Petersburg University for their work, for their assistance in conducting experiments, for valuable advice, and of staff of Resource Center who helped us out with some equipment we needed for our experiments, and big thanks to all employees of the physics faculty who gave me knowledge during all these years and prepared me for this important test. And many thanks to my academic advisor, Yuri Borisovich, who made the biggest contribution to this work, and I hope that we have a lot of work ahead of us. And a big thanks to all my family, to my significant ones who always support me. Thank you very much, everybody. Thank you, Aleksei. On behalf of the Council, let me once again congratulate you on successful defense of your thesis, and let me wish you future success with your work. And It's my first time in this remote access mode, and I was a little bit nervous about how it will go, because there is an important thing connected with Aleksei's. It's the last day he can apply for support of young scientist support program. So hopefully he will submit his application today, and I hope that Aleksei will continue his work at the Faculty of Physics, and then he will have another 5 years or maybe more to conduct his research. So let me once again congratulate Aleksei, and I hope that you will live up to our expectations in the future, and we look forward to hearing your wonderful works and your achievements, scientific achievements. Thank you. I declare the session closed. Thank you everybody for your participation. Thank you, and stay healthy. Thank you.